Thanks for coming on. Each week I'm going to release a YouTube video going through my revision sheet from the previous week. Hopefully you've already had a chance to do these questions. If not, pause your video, give them a go now. Okay, question 1, parametric equations. Now the first thing I see quite often from my pupils is feeling the need to make t the subject. That's not what I would do when I'm solving these. I think it's really worth taking your time to look at these equations carefully and look for some common features. Okay, I think it's obvious they've both got an e to the t. Okay, so rather than making t the subject, I'm going to ignore that, and instead I'm going to recognize these equations have an e to the t. I'm going to try and see if I can use that to avoid a little bit of unnecessary manipulation. If I take this x equation, x equals e to the minus t over 4, that follows that x equals 4x equals e to the minus t, and I can reciprocate both sides. So I can say e to the t equals 1 over 4x. Okay, so if I can find where I can substitute e to the t into my first equation, my y equals, I can just substitute out e to the t. I've eliminated e to the t. I'll be in Cartesian without making t the subject. So if I relook at my y equals e to the 3t minus 4, hopefully we're happy with laws of indices. Y equals e to the t all cubed minus 4. And actually I have an expression for e to the t over here in Cartesian form. I can substitute that straight in. I can say y equals 1 over 4x all cubed minus 4. Okay, that's Cartesian form. I didn't tell you what form to put it in, so it'd be tempting to stop there. I would probably at least cube that bracket. So I've got 1 over 64 x cubed minus 4. Okay, happy with that. Question 2, solving trig equations. I've tried to start with some more straightforward questions to get you going quickly this week. I hope we've seen trig equations quite frequently, and we should recognize straight away that the real issue in this question is that you have different trigonometric terms. Some are in sec, some are in tan, so we need to use one of our trig identities to eliminate one of those. If you can't already remember them, I always start with this one, sine squared x plus cos squared x equals 1. Okay, I know I would like a sec squared. It's usually our squared terms we can eliminate. Sec is 1 over cos, so I'm going to think about dividing all of these by cos squared. Okay, cos squared x, cos squared x, cos squared x as my denominator on all three terms, dividing 3 by cos squared x. Okay, simplifying that gives me sine over cos is tan squared x, cos over cos is 1, and 1 over cos is sec squared x. Okay, so I can use this trig identity. Okay, substitute in. Actually, I've already got sec as the subject, so I can substitute in my sec squared over here, and then I'll have all of my terms in tan. So sec squared is tan squared x plus 1. Okay, so that's my sec squared x there, plus 3 tan x equals 1. I'm now looking at this a little bit like a quadratic. I've got some squared terms. So I'm going to collect everything on one side. This gives me tan squared x plus 3 tan x equals 0. Okay, that's nice, that factorizes. Tan x plus 3 equals 0. Okay. Either of my factors could be equal to 0. So I want to know, when is tan x equal to 0, or when is tan x equal to minus 3? Okay, well, I'm just going to quickly think about a tan curve. Okay, tan x equals to 0. I'm not going to bother with a calculator. I can think about where the roots of this equation are. Okay, so tan x equals 0 leads me to x equals 0. Okay, these roots are pi apart, or x equals pi, or I could go back the other way. There'll be a root over here too, minus pi. Okay, tan x equals minus 3. I'm going to need to use a calculator. So I've got this here. I'm going to use tan minus 1 minus 3. This leads me to an answer in degrees. I'm obviously working in radians. Change that to radians, and I get minus, so x equals minus 1.249. Okay, so that's given me an x value over here relating to minus 3. I can add or subtract pi onto that to find other solutions. If I subtract pi, I'm going to be outside of my domain, which is up here. So I'm going to add pi onto that. Get 1.89. Okay, I like to put all of these together as one clear solution and in order. So I have minus pi minus 1.249. I should put a 3 on there to go 3 decimal places. I have 0, have 1.893, and I have pi. Okay. Right, on to question 3. So solving mod equations. I would always recommend starting with a diagram. Okay, with mod equations, at least get an idea of what's going on. I'm saying equations, of course I mean inequalities. I would think about plotting 2x plus 3, which comes up like this and would continue down below the axis, but the mod is going to bring that up there. And I would like to know when this is greater than 3. So at the moment I've plotted y equals the mod 2x plus 3. And I would like to know when is that greater than the value 5. Okay. Obviously that intercept's only at 3. So my 5 should probably be a little bit higher up if I'm thinking about my scale carefully. Okay, so I'm going to go ahead and solve this. With mod equations, I would like to know either when is the positive part of this equal to 5, or when the negative part of my mod is equal to 5. Okay. I'd realize here I'm using equations. So strictly what I'm doing is I'm finding kind of critical values. I'm finding where do these lines meet, and then I can think about my inequality at the end. Okay, solving this first one, 2x equals 2, x equals 1. This one, 2x equals minus 5 minus 3. Okay, just dividing by minus 1 and move my 3 across. X equals minus 4. So that kind of tells me these two values. X equals minus 4 and x equals 1. Okay, I need to be careful with the fact I'm thinking about an inequality. I like to use my diagram and just recognize. Okay, I'm looking for the set of values when this curve's greater than 5. Okay, well that's 2 parts of the curve. I'd expect 2 inequalities. put my diagram together with these critical values, I can see this is true if x is greater than 1 or x is less than -4. Okay, question 4. So, in this question, as soon as it mentions a normal, we should be thinking about hopefully finding a gradient. Okay. I would also recognize that the x and y terms are tied up together a little bit. We have this xy term being multiplied. It doesn't feel particularly tempting to make x a subject or y the subject in this question. Okay, that immediately makes me think about implicit differentiation. Okay, so I'm thinking about differentiating every term. If it's a y term and I'm differentiating with respect to x, I need to remember to multiply by dy dx. I also need to remember things like product rule for something like x plus y. Okay, so differentiating x plus y, I have product rule. I'm going to differentiate the first part. X differentiates to 1, multiply it by the second part. Okay, 1 multiplied by y is y. I'm going to look at that again. I'm going to differentiate the second part. Y differentiates to 1 multiplied by dy dx, which is dy dx, multiplied by the first part, which is plus x dy dx. Okay, it would be tempting for some people to stop and do product rule using u and v and then finding u dash and v dash. And sometimes that might be helpful. To be honest, I would try and get to a point where you're confident doing something like product rule quickly and efficiently without feeling need to stop and doing it formally. Okay, so I've differentiated that first term. Gonna move on and look at my second term, y squared. Y squared differentiates to 2y. Differentiate a y term, multiply by dy dx. My third term, 3x, differentiates to 3. And my final term, minus y, differentiates to minus 1 multiplied by dy dx. My right hand side is equal to 0. Okay, so implicitly differentiate. This is going to be helpful because I can find my derivative. Okay, I'm going to think about collecting those dy dx terms together and factorizing them out. What I noticed looking at this, again, it's worth taking your time to look at these expressions before you kind of rush into what you're doing next. I noticed this term here is the only negative term. So I'm going to think about moving these 3 terms with dy dx onto my other side of the equation, which is going to give me y plus 3 equals x dy dx plus 2y dy dx minus dy dx. Factorizing that out, I get y plus 3 equals dy dx multiplied by x plus 2y minus 1. And that lets me come up with an expression for my derivative. Dy dx equals y plus 3 divided by x plus 2y minus 1. Okay, so that's my derivative's kind of an expression for the gradient at any point. I'm looking at the normal at a specific point. I'm looking at normal when x equals minus 1 and y equals 3. Okay, so I would go ahead and substitute those in, and I would realize that if you're substituting values into a derivative, I'm kind of not really talking about a derivative. I'm now talking about a gradient at that point. Okay, y is 3 plus 3 for my numerator. X is minus 1 plus 2 lots of my 3 minus 1. Okay, my numerator is 6. My denominator is 6 to equal to is minus 4. My gradient is minus 3 over 2. Okay, So that's my gradient of the tangent at that point. Okay, if I've just substituted those values into my derivative, that's the gradient of the tangent. Okay, which leads me to finding my gradient then of normal when x equals -1 and y equals 3. Okay, that's going to be the negative reciprocal of that gradient there, so they should have a product of 1. This gradient is going to equal, I'm going to call this M1, 2 over 3. Okay, so I can find, if I have a gradient and I have a point, I can find the equation of my normal. Equation of normal. So y minus y1. So y minus 3 is going to equal 2 over 3 x minus x1, which is -1. Okay, so I'm going to bring that up here. So I had y minus 3 equals 2 over 3 x plus 1. That's the equation of my normal. Okay, so I now need to think about the actual wider question. The normal meets the x-axis at the point A, the y-axis at the point B. And I want to find the area of the triangle OAB, okay, where O is going to be the origin. So I obviously want to find the coordinates of A and B, so I'm going to go ahead and I'm going to think about them. So A is on the x-axis, so A is when, if it's on the x-axis, y equals 0. Okay, so I can substitute y equals 0 into this. Minus 3 equals 2 over 3 x plus 1. Minus 9 equals 2x plus 2. X equals minus 11 over 2. Okay, so A as a coordinate, I know it has an x value of minus 11 over 2 and a y value of 0. Okay, I can think about the coordinate B. B was when the normal met the y-axis, so that's when it has an x coordinate of 0. Again, I can substitute that in. I can say y minus 3 equals 2 over 3 times 1. So y equals, adding my 3 across, which is kind of 9 over 3 plus 2 over 3 is 11 over 3. Okay, so I'm now going to think about this question, finding the area of the triangle. In fact, let's write B down as a coordinate. B is the point where x is 0 and y is 11 over 3. So I have a coordinate axis, some normal curve that is y minus 3 equals 2 over 3x plus 1, which would look something like that. I have a coordinate b when x is 0, which has a value of 11 over 3, and a, I've drawn this diagram the wrong way around. Okay, so I'm now going to draw this diagram, think about where O, A and B are. So I've got a coordinate axis. I know B has coordinates 0 and 11 over 3. It's going to be up here somewhere. A has coordinates minus 11 over 2, 0. It's going to be over here somewhere. I'm thinking about triangle ABO. So that's a nice right angled triangle. So it's going to have an area equal to 11 over 2 times 11 over 3 divided by 2. Okay, half base times height. Okay, well, 2 times 3 times 2 is 12. 11 times 11 is 121. Okay, question 5. So, as soon as you see an integration question, you should start to kind of cycle through your different methods. And I think something a lot of people would have seen to begin with is that you kind of have two terms and a product. So I think a lot of people would have been tempted by integration by parts, which is definitely what I think about when I see a product. And it might get you there. It's not the method I would choose. I would look at this and kind of recognize inverse chain rule. Okay, I like to think about that. What I'm recognizing here is I have the derivative of some function and some other function to some power. Okay, sine to the power of 5 multiplied by the derivative of sine is kind of what I'm recognizing here. As soon as you see that, the kind of a function multiplied by its derivative, chain rule should come to mind. And I like to do chain rule just by kind of starting with some function and differentiating. And see if I can land on something near that integral. Okay. So when I'm differentiating, I often lower my power by 1, which makes me think I want to start at sine to the power of 5x. Okay, and actually, for a moment, I'm just going to think about that power of 5 as being outside the whole function. Sine x all to the power of 5. Okay, they're equivalent. So if we're good at chain rule, we know that the power comes down, give me a 5. The derivative comes out, sine x differentiates to cos x, and then the power lowers by 1. Okay, so I like to think about some function that differentiates to get me pretty close to what I was actually looking at in my integral. Okay, now what I like about this is I can see exactly like the coefficient I would want, that if I can give my integral a coefficient of 5, I know exactly how it integrates. It integrates exactly to sine x to the 5. I often see pupils skip this step and go straight to integrating. I like to play around with coefficients first. I like to say, actually, let's write my integral back out. And let's write it with that coefficient I want. Okay, I want a 5 in there. Okay, but I need this here, to be equivalent to the thing I'm actually integrating. Okay, I've gone ahead and multiplied it by 5. So for them to be equivalent, I need to kind of cancel that out with my 5th on the outside. I can see that I have the thing that integrates back to sine to the 5. So carrying that integral out, I have a 5th sine to the 5 x between 0 and pi on 3. Substituting those in, I have a 5th of sine to the 5 pi on 3 minus a 5th of sine to the 0. Sine 0 is 0, just thinking about a sine curve there. A lot of people probably typed this one into their calculator if they got this far. Again, I'm just going to think of this as sine to the pi on 3 all to the power of 5. Okay, I think if you do that in 2 steps, you'll probably get an exact value because pi on 3 is something we can manage. I'm going to quickly jump to my calculator. Sine pi divided by 3, which is root 3 over 2. And then I want to raise that. I want to raise my answer to the power of 5. Okay, so I have... it didn't like doing that exactly. Well, we can do that quickly. So we've got a fifth of root 3 on 2 to the 5, which is a fifth of 2 to the 5 will be 32. Root 3 to the 5, if I think of the fact like root 3 squared is 3, root 3 squared is 3 again, and then there's one more root 3. I'm kind of thinking that as root 3 squared times root 3 squared times root 3 being power of 5. Okay, well those two are 9. Another one is root 3, so that's 9 root 3. Nothing there cancels between my 9, 5 and 32. That's going to be exactly 9 root 3 over 160. Okay, I imagine a lot of people did it exactly. Did it in their calculator and didn't get it exactly, which is fine. I didn't really specify. But if you notice that could be done exactly, that's what you should have got. The rest of you probably got 0.097 that I'll put up there for you as well. Okay, question 6. This is our binomial expansion question. I would realize straight away that there's kind of two things tied up in this root. Okay, we have the root of 1 plus x over 1 minus x. And I kind of want to think about, normally when we do binomials, we just have like one bracket and one power. So I want to split this up into individual brackets. I'm going to think of this as 1 plus x to the half, okay, which is the root of my numerator, and 1 minus x to the half as my denominator, but I need to recognize that's been like reciprocated to bring my denominator up here, so that's minus a half. Just thinking about the problem as a whole before I dive in and do some expansion, what I'm thinking is I have two separate binomial expansions to do here and they're being multiplied together. So if I can expand my first one, kind of express that in a big bracket with a bunch of terms in here, and I can multiply it by my second bracket expanded, I can then just multiply these out as a pair of brackets to think about this bigger function. Okay, so I'm going to think about these two things kind of as individual units. First, I'm going to think about that expansion on its own. Okay, binomial expansion, hopefully we know, is 1, well, it's in your formula book anyway, plus nx plus n minus 1 over 2 x squared plus n minus 1 n minus 2 x cubed all over 2 times 3. Okay, so I'm going to look at doing this where I have an x of just x and an n of a half. So I've got 1 plus a half of x plus a half times a half subtract 1 is minus a half times x squared all over 2 plus a half minus 1 half minus 2 over 2 times 3 is 6 x cubed. Okay, I like to acknowledge that series carries on. Okay, simplifying these, I have 1 plus x over 2 plus, okay, I've got a positive and a negative, so it's not going to be a plus, it's going to be a minus. Half times a half divided by 2 is an 8th x squared. Okay, this one I've got a 3 on my numerator. I'm going to cancel that with that 6 to bring it down to 2. So I've got 2 divided by 2 divided by 2 divided by 2. Okay, so I've got a 16th and I have 2 negatives. So it's going to be plus a 16th of x cubed. Okay, that one looks good to me. So I'm going to go ahead and go on to my second binomial expansion of 1 minus x to the minus a half. Okay, this time I've got an n of minus a half, and actually my x term's this minus x. So I need to be careful of what impact that has. So going up to my formula, I have 1 plus nx. X is minus x, so I've got minus a half times minus x there, plus minus a half minus 1 all over 2 nx squared. Okay, I'm just going to stop and talk about this term really quickly. This is the most common mistake I see on this, of these terms here, where people forget to apply their power to their coefficient. Okay, that x has a coefficient of minus 1. So when I'm squaring my x term, I need to recognize that that minus is going to get squared as well. It's in with this power. Okay. Recognize the use of a bracket there to kind of minimize that mistake. My cube term plus a half minus 1, a half minus 2, divided by 2 times 3 x cubed. Okay, simplifying these, I've got 1 minus and a minus, I have plus x over 2. This one I have a minus squared and then 2 minuses in my coefficients. So again, that's even number of minuses, and that's going to be a positive term. I have a 3 on my numerator and 3 2's on my denominator, so it's going to be 3 over 8 x squared. Okay, this one I've got minus x cubed and then 3 minuses out front, and that's 6 minuses altogether, so it's going to be a positive term. I'm going to cancel those 3's. I've got 4 2's on my denominator, 5 on my numerator. That's 5 over 16 x cubed. Okay, so now I have these two things individually. I can go ahead and think about this question as a whole. 1 plus x, 1 minus x is approximately equal to, which I probably should have used on all of these expansions. It's approximately equal to the product of these two individual expansions, which is 1 plus x over 2 minus an eighth of x squared plus a 16th of x cubed multiplied by 1 plus x over 2 plus 3 over 8x squared plus 5 over 16 x cubed. Okay, now I'm just thinking about expanding these out to find up to my x cubed terms. So this is approximately equal to, well, my constant is just going to be 1 times 1. Okay, I'm just thinking about like double brackets but with more terms in them. 1 times 1 is 1. Okay, my linear terms, I'm going to get 1. I'm just thinking about multiplying 1 by x over 2. And I'm also going to get that going the other way, 1 times x over 2. Okay, so I have a half of x and a half of x. Add those together, I get an x. Okay. My x squared terms, this is where they start to have a few more terms coming together. So I'm going to have 1 multiplied by 3 over 8x. Okay, so I've got 1 times 3 over 8. I have the term going the other way round, so I have 1 multiplied by minus an eighth. I have 1 times minus an eighth. And I also have in this term, my squared terms, I need to think about the fact this x squared term could come out of my x term over here multiplied by my x term over here. So I have a half of x times a half of x. Okay, recognise what I've done here, which is just to think about all the things that multiply to give me an x squared as coefficients, and kind of factorise the x squared out. Okay, that's how many x squared terms I'll have. My x cubed terms, I'm going to have, right, let's get rid of this red. My x cubed terms, I'm going to have my constants multiplied by my x cubed terms. So that will give me 1 times 5 over 16 and 1 times 1 over 16 going the other way. I'm also going to have my linear terms, like my x to the power of 1 terms, multiplied by my squared terms. So I'm going to have x over 2 times 3 over 8 x squared. That'd give me an x cubed. So that's going to be 3 over 16. And I'm going to have the same going the other way. I'm going to have my x to the 1 on this side multiplied by my x squared on this side. Okay, which is 3 over 8x squared. Sorry, my x over 2 times my 1 over 8x squared, which is going to be minus 16th x cubed. Okay, tidying those fractions up. This expansion is equal to 1 plus x. Okay, so I've got 3/8, take away 1/8, which is a quarter, plus another quarter. Quarter plus a quarter is a half. So I've got x squared over 2. And this final one, and they're all in 16ths, so I've got 5, 8, 9 16ths, take away 1 16th is 8 16ths, which is x cubed over 2. And again, this is just the start of an infinite series, so I can recognize that. Okay, question 7. This here question on the old spec I think would have been broken into part A, part B. And in the new spec they're expecting you to recognize the skills. Okay, so you have to take a little bit of time to look at this and see what skills you have that kind of apply to this problem. First thing I would recognize is this 3 cos x plus 4 sin x is something that we could kind of manipulate to look a little bit differently. Okay, I'm going to go ahead and tell you what I think the old spec would have done. It would have had part A express 3 cos x plus 4 sin x in the form r sine x plus alpha. Okay, it would have just straight away revealed to you that this is a harmonic form question. Okay, you're not going to have that luxury anymore. But what you can do is just start to question yourself every time you see some sines and cosines added together. Would harmonic form be helpful, and why would it be helpful? Okay, now in this question, straight away I'm thinking it'd be helpful because if I only had one piece of trig there, and I could think about that behavior of that piece of trig, okay, as in what's its biggest value, what's its smallest value, I'd be able to think about the whole function by thinking about that one bit of trig. Okay, that's much harder to do when there's these two bits here. Okay, but I'm going to go ahead and just do this like a two-part question for now, because that's how I would have laid my working out. I'd have just dealt with the trig harmonic form, then dealt with a bigger function later. So I want to recognize that 3 cos x plus 4 sin x is equivalent to r sin x plus alpha. I'm going to go ahead and apply my addition formulae, which is in your formula book if you need it. to my right hand side, which gives me r sine alpha cos x plus r cos alpha sine x. I can compare coefficients here. I can see that I've got r cos alpha as my sine x coefficient, which is the same as that 4. And I have r sine alpha as my cos x coefficient, which would be the same as that 3. Okay, so that leads me to the following. It leads me to say r cos alpha equals 4, r sine alpha equals 3. Dividing those two terms, my bottom one by my top one, I'm going to get that tan alpha equals 3 over 4. I'll be able to find alpha. I'll do that on my calculator in a moment. I'm also going to quickly jot down that r squared equals 3 squared plus 4 squared. Okay, I would just think of using Pythagoras in this scenario. Okay, Pythagoras for those two numbers will find you r. You can show that by squaring all of these things and add them together, but I would do this quickly. Hopefully we'll recognize Pythagorean triple, and we know that r is 5. Okay, so jump into my calculator. I want tan minus 1 of alpha. I want tan minus 1 of 3 divided by 4 to find alpha, which is equal to 0.64. Just realised I didn't tell you whether to work in radians or degrees, but I'll do it in radians. Shouldn't matter too much if you've done it in degrees. So I can now express that. I can say that 3 cos x plus 4 sine x is equivalent to 5 sine x plus 0.64. Okay, I'm now going to go ahead and think about my bigger function. I can say that f of x is equal to 1 divided by 7, looking back at the function, plus 3 cos x plus 4 sine x, but I know that part is equal to plus 5 sine x plus 0.64. Okay, now I'm thinking about the behavior of this part here. Okay, this 5 sine x plus 0.64. If we know that sine x bounces between 1 and minus 1 at its maximum and minimum points, okay, if I then multiply that all by 5 and look at the plot of, so this is sine x, and I think about this plot 5 sine x, okay, I can think about this as being a bigger version stretched vertically up to 5 and down to minus 5. Okay, so that part of trig I've labelled red, I know it must have a value between 5 and minus 5. So now I'm thinking about the bigger impact that has on this function. Okay, I'm thinking in my head. Okay, this bit I wouldn't really write down, but I'm thinking about what happens when you substitute in the different values this function can take, or some of the different values. Okay, I would certainly think about these three fractions. Okay, thinking about kind of 5, minus 5, and 0 being some of the key values that could come out of 5 sine x. And then I can actually answer the question and think about, well, which of these gives the minimum value for this function? Well, they're all positive. I want the fraction to be, sorry, not the minimum value, the maximum value of this function. Well, that's going to be when the denominator is as small as possible. Okay, which is obviously this one here. Okay, so actually I'm going to get f of x equals 1 over 7 minus 5, which is a half, being the maximum possible value, maximum. Okay, the other part of the question asks for which value of x does this maximum occur. Okay, so I would just kind of go through that logic we just used. When's this maximum actually happening? This maximum's actually happening when our 5 sine x plus 0.6 is coming out as minus 5. Okay, well that's going to happen when sine x plus 0.64 is actually coming out as minus 1. Okay, well we can think about a sine curve. I'm already thinking about the fact I want the first positive solution was in the question. Okay, my first positive x value, minus 1 comes out when x is equal to 3 pi on 2. Okay, so x plus 0.64. Okay, you could sign minus 1 each one. I like thinking about the key values without using a calculator. Comes out at 3 pi on 2. So the first positive x, if we subtract 0.64 from both sides, this time I am going to have to use a calculator, which I appear to have lost. 3 pi divided by 2 minus 0.64 is equal to 4.072. Question 8. So we're producing a plastic storage box. I think the question kind of implies that that's going to be a cube. Oh, sorry, cuboid. They want a storage box where the volume is equal to 100 centimeters cubed, and it has a fixed height, 10 centimeters. It wants us to find the least amount of plastic that could be used to make this, and to actually show that that would happen when the base and width are equal. Okay, so they're saying that the height is fixed, but the base and width are variable. Okay, so I'm going to think about calling them x and y. That's just kind of my intuition. As soon as things are variable, just throw some algebra in there. But I'd realised with this question, I can actually come up with an expression for the volume being 10xy, and the volume itself is 100. So actually I could eliminate one of them variables. I could say y equals, dividing by 10x, 10 over x. I could go ahead and make this a one variable problem. Okay, so I'm looking at a cuboid, very badly drawn cuboid, with a height of 10, a base of x, and a width of 10 over x. So I would like to know the least amount of plastic that could be used. Okay, so the amount of plastic used in producing something is going to be kind of a product of the surface area, or a function of the surface area. So I'm just going to think about the area of this. When can I get the minimum area of this, and hopefully show that the minimum occurs when these two things are equal. Okay, so if I come up with an expression for my area is going to be equal to this face here, which is 10 times x times 2, because there's 1 on the back as well. Okay, I've got this face here, which is 10 times 10 over x, which is 100 over x, and there's 2 of those faces. It's 200 over x. And my face on the top, which is x times 10 over x, which is 10, and there's 2 of those. So I've got an expression for my area. I'm thinking about minimum area. So as soon as I'm thinking about minimums, I would like to know for which values of x is that minimum going to occur. I'm going to think about differentiating a in terms of x. So I've got 20x, which differentiates to 20. I've got 200x to the minus 1. Okay, I'm just thinking of that as 200x to the minus 1. So differentiating it, the minus 1 comes down. Got minus 200x to the minus 2. And 20 differentiates to 0. Okay, I would like to know for what values of x is this at a minimum. So before I think about a minimum, I'm just going to say when's it at its stationary points. Well, it's at its stationary points when dA dx equals 0 is a stationary point. Okay, so I'm going to set that to 0. 0 equals 20 minus 200 over x squared. Okay, well, timesing through by x squared, I get 0 equals 20 x squared minus 200. Divide by 20, 0 equals x squared minus 100, sorry, minus 10. And factorising gives me x plus root 10 or x minus root 10. Which leads me to x equals root 10. I can ignore x being a negative because we're looking at side lengths. Okay, so at this point, I've shown that it's a stationary point. I found the value of x for which it's a stationary point, which is root 10. I'd like to go a little bit further and check that that's a minimum. I suspect it is, but I need to actually show that in this question. So if I want to think about minimums, I should take my derivative, which we had before, as 20 minus 200 x to the minus 2, and I can differentiate this again to give me the second derivative of a being equal to 20 differentiates to 0, minus 2 comes down, 400 x to the minus 3. Okay, I only really want to know if this is greater than 0 or less than 0. If it's greater than 0, it would show that it's a minimum point. Okay, so I want to substitute sub x equals root 10 into my second derivative of a. So my second derivative of a is equal to 400 over root 10 cubed. Well, root 10 squared is 10, so we've got 400 over 10 root 10, cancelling out a factor of 10, reciprocating times top and bottom by root 10. I think we're going to get 4 root 10. Okay, and importantly, that's greater than 0. Shows I have a minimum. Let's concluding those two things together. Let's say when x equals root 10, my derivative is equal to 0, and my second derivative is greater than 0. Therefore, area is a minimum. Okay, I've nearly done answering the question. The last part of the question was just show the base and width are equal at the minimum. So I now have the x value where the minimum occurs. My base was equal to x, which is root 10. My width was equal to 10 over x, 10 over root 10, which is root 10. Therefore, to finish, base equals width at minimum area. So if you've made it this far, great work. Well done doing the sheet. There's another one available now on my Twitter. Again, same time next week, I'll be posting the solutions up on YouTube. Keep up the good work. Thanks very much.